So we have a lot of different frameworks in which we make discriminations or we impose intervals. And we're not very good at discriminating the frameworks, and we have all kinds of metrics and measurements within different frameworks, and we tend to conflate them or forget to discriminate them in the first place, get them confused, and so on. But there's a kind of a universal sort of metric, and it's interesting that we think about it we think about distance and measurement in a kind of backwards way, especially when we compare our habits to how physicists are able to think of it. And the way that physicists think of it is probably important for us. So I think we can learn something just from changing our perspective on distance and frameworks. And I found these two little chapters in this book, Relativity and Common Sense, A New Approach to Einstein by Hermann Bondi. It was published in 1962. And I'd like to just read them to you. The first one's called Using Radar to Measure Distance. A special application of short radio waves that is of great importance in war and peace and of considerable interest to the physicist is radar. As is well known, the notion of radar is that you transmit a short pulse of radiation which bounces back from the target, and the wave received gives one information about the distance and direction of the target, the direction being simply that in which the wave had to be sent out to be received back. Of particular interest to us here is the manner in which the distance of the object is found. What one does is to measure the interval of time between the transmission and the reception of the pulse. Since one knows that radio waves travel with the speed of light, this interval multiplied by the speed of light gives one the total length of the path traveled by the packet of waves, which is to the target and back, and thus twice the distance of the target. The great interest of the principle of this method of measuring distances is that one does not use a yardstick. No standard meter or standard yard is employed. What one does is to measure an interval of time and then multiply this by a quantity, the velocity of light. We can then speculate a little about the true nature of distance. It is often very useful in physics to try to get away from the particular circumstances of our existence, in which certain materials are cheap and others expensive, in which the temperature variations are small around a mean temperature that is far removed from the very cold of space or the very hot of the stars, and so on. In the present instance, we want to make only a very simple assumption. We shall suppose, for the moment, that the makers of radar sets have managed to become so much more efficient than the makers of yardsticks, that instead of rulers, one normally employs a radar set, measuring the time between transmission and reception of a pulse. If, then, we had grown up measuring distances through the measurement of times, if we had grown up without using inch tapes and the like, then I should guess that the whole notion of a scale of distance would not occur to anyone. Now, what he's saying is that there would be no parts to distances. There would be no scales of distances. The next chapter is the units of distance. One would always use time to express distance. This, of course, is done to a considerable extent in astronomy, where, to get away from the awkwardly big figures arrived at otherwise, we measure the distances of stars in light years. That is, the distance light travels in a year. But there is no reason why this manner of expressing distances should be confined to the very large astronomical distances. We could speak of light microseconds. That is, the distance light travels in a microsecond, a millionth of a second. This distance is about 300 meters or 330 yards, and is quite a convenient unit. A light millimicrosecond would then be a thousandth of this unit, and would be roughly equal to a foot in length, and so on. If we imagine, then, a civilization in which the yard or meter is unknown, and every distance is expressed as light second or light millimicrosecond, or whatever the case may be, then the members of that sort of civilization would look at one very blankly if one asked them what the velocity of light was. They would not regard this as a quantity to be expressed in meters a second or miles a second, as the case may be, but simply as a unit, the natural unit of velocity. Velocity 1 would refer to as an object, velocity 1 would refer to as an object moving as fast as light. All ordinary velocities would be expressed in terms of this standard. Thus, the velocity of a jet plane would be around 1/1,000,000th. That is to say, a jet plane takes 1,000,000 times as long to get from one place to another as light does. Similarly, a train or fast car might have a velocity of 1 part in 10 millions, 67 miles per hour approximately. In other words, by accepting the natural standard of velocity, the velocity of light, this civilization would have done away with the need to register both a standard time and a standard distance, and to use the awkward translation figure of the velocity of light. There would only be a time standard, and in this civilization, which would make life rather more convenient, and its members would regard us as people who work with distances and times in the most complicated and absurd way. Perhaps it might be worthwhile here to describe an alternative civilization, which has the same relation to ours as we have to the one just imagined. This is a civilization in which the direction north and south is regarded as holy and is measured always in miles, whereas the direction east and west is regarded as perfectly ordinary and profane and is always measured in yards. If people had been brought up to look at things that way from an early age, it would require a daring mind to suggest that there was some connection between distances north and south on the one hand, and east and west on the other. And physicists would be employed to work these things out and would then arrive at the remarkable result that 760 yards of the east-west measure were, in some sense, equivalent to the mile of the north-south measure, and this figure of 1760 would acquire a sacrosanct meaning there, a little as the velocity of light has for us. Of course, we must imagine that in this civilization, their national physical laboratory would keep two quite different standards, a standard mile for the measurements of north-south directions, and a standard yard for measurements of east-west directions. This would look absurdly complicated to us and unnecessary, but this, I am sure, is what we would look like to the civilization about which we talked earlier. The physicist has no hesitation in jumping to the simpler conclusion, and immediately agrees, then, that there is really no point in using a standard of distance. All we need are standards of time. Again, there is the question as to what the value of the velocity of light is. The velocity of light, of course, is unity by definition. What we call measuring the velocity of light would seem to him a complicated and roundabout way of determining the length of the standard meter in Paris in terms of the well-known public standards of time. It's a fascinating little play on how metrics can be incredibly confusing and breed frameworks where there aren't any due to, how shall we put it, preconceptions of perspective, purpose, approach, or the framework in which we are asking or examining questions.